This is Unit 4, Objective 3 for AP Calculus BC, and we're just starting to do volumes of rotation. And our focus for this lesson will be rectangles that are perpendicular to the axis of rotation. Okay, so in theory here, it's like if I have some y equals f of x, and if I'm rotating about the x-axis, so notice I've got my arrow showing the direction of the rotation here. We have to have, at least for right now, we have to have rectangles that are perpendicular to the axis of rotation. We're going to start off with rectangles that are touching the axis of rotation at one end that whole time. So if that is occurring, if you focus in on that one rectangle, if it rotates about the x-axis, we're getting a disc shape, okay, and a disc or a coin kind of shape. And if you think about a disc or a coin, isn't it just a little itty bitty cylinder? Okay, and how do we find the how would I find the volume of that cylinder? The volume of the cylinder is the base area times the height. The height is the thickness of the coin, so it's either going to be a delta x or a delta y. If they're vertical rectangles, then it's a delta x. If they're horizontal rectangles, then it's going to be a delta y. And the area of the base is a circle. Okay, and so really this is pi r squared times the height, which is delta x or delta y, really is what it's boiling down to. And so as we're doing that, in this particular case, the radius is always from the axis of rotation to the rectangle. Now, since the rectangle is touching the axis of rotation the whole time, so in other words, to the far side of the rectangle. So the radius, top y minus bottom y, the radius would be f of x in this case. And so the volume, definite integral, because we're going to sum up all the sum of all these disks as we're doing it, and we're going to do the definite integral from a to b, because everything's in terms of x's here. If I'm doing vertical rectangles, little delta x's, so it goes from left to right, from a to b, and don't forget we're going to be doing pi r squared times delta x. So pi, now r is f of x in this case, so f of x squared, and delta x, as we make the transition from pre-calculus to calculus, the delta x becomes a dx. So essentially, I mean, this is what we're doing here with this one right now. Obviously, the pi could be brought out in front, but that's what we would do for this particular one. Okay, now let's do an actual example here. So the region bounded by y equals square root of x, y equals 0, which is the x-axis, and x equals 4. Okay. If we wanted to, we could kind of highlight that region. Okay, so I've drawn in a sample rectangle. I like to label the endpoints here. So, and I've also got the fact that we're rotating about the x-axis, so I've got the curved arrow. Yes, you need to have that. Okay, so my radius is right here, and it's root x top y minus the bottom y. So the radius is root x minus 0, in other words, root x. Okay, so the volume is going to be the definite integral from, okay, so start at the furthest left we can go, because we're doing little delta x's, so everything's in terms of x's. So from 0 to 4, pi r squared, so root x squared, and delta x, so dx. Okay, there's the setup. Now let's bring the pi out in front. and we have 0 to 4. Root x, if we square it, is just x dx. So we have pi times 1/2 x squared. So pi over 2x squared evaluated from 0 to 4. And we would get pi over 2 times, let's see, we got 16 minus 0. And so we have 8 pi is the volume here. Okay, let's try another one. I guess I have to switch pages. Okay, so problem number 2. Let's say we have y equals cosine x, x equals 0, y equals 0. So essentially it's the first part of cosine from 0 to pi over 2 that's up there in quadrant 1. And we're rotating about the x-axis. Okay, so I've got my arrow drawing showing that I'm rotating about the x-axis. We are only doing perpendicular rectangles to the axis of rotation for today, for this assignment. So vertical rectangles, since I have a horizontal axis of rotation. My radius is cosine x minus 0. So my volume, rectangles, everything's in terms of x's, so it starts farthest left for the region and goes to the pi over 2, so it goes from 0 to pi over 2. Pi, now I can bring the pi out in front. Pi radius cosine x squared dx, pi r squared delta x summed up from 0 to pi over 2. Okay, so we go ahead and now the setup really is the new stuff here. I mean, once we've done that, now we just continue on. How do we integrate cosine squared x again? Oh, it's one of those half angle formula substitutions. So we have, let's see, I'd have 1/2 0 to pi over 2, and we'd have 1 plus cosine of 2x, okay, dx, and so we have pi over 2, and I would get x, and cosine is the derivative of sine, so plus sine of 2x, but the derivative of the guts, the derivative of 2x is 2, so we need an adjustment for that. Okay, 0 to pi over 2. So we have pi over 2 times, okay, if I plug in a pi over 2, I get pi over 2 plus, okay, now 2 times pi over 2 is pi. Sine of pi is 0, so that's 0. Minus, if I plug in a 0, I get 0. And 2 times 0 is 0, and sine of 0 is 0. So we have pi over 2 times pi over 2, in other words, pi squared over 4. Okay. Same region as number 2. This time rotated about the y-axis. Okay, so going about the y-axis. Okay, so I'll go ahead and show that I'm going about the y-axis. Now, some of you might be saying, okay, did I have to draw it that way? Could I have gone the other direction? Yeah, it just you need to show the curved arrow that's going around the y-axis there. Okay, I've got, now this time, my axis of rotation is vertical, so perpendicular to that would be horizontal rectangles. And horizontal rectangles means that everything has to be in terms of y. Everything has to be in terms of y. So now let's start over here on the left side of the rectangle because that's easier. So the x is 0 and the y is y. Now the x over here, okay, well, let's see. What does x equal in terms of y? Well, if I do inverse cosine, that's what x is equal to. So inverse cosine of y, comma, y. And so my radius, right side minus left side, okay, radius is inverse cosine of y minus 0. So inverse cosine of y. Okay, so my volume is pi r squared. Now r is inverse cosine of y. So inverse cosine of y squared dy is the volume of the cylinder, so delta y or dy. Limits of integration. Okay, my rectangles start, it's y values, so I have to start at the lowest elevation and they go to the highest elevation. So lowest elevation for this region is 0, highest elevation is 1, so 0 to 1. Okay, now inverse trig functions. We don't know how to do derivatives or integration with them yet, so if we were to have something like this right now, we would have to have graphing calculator accessibility. Okay, and so really that's what it comes down to right now. Now, in another couple of units, or maybe one more unit, I forget which, we'll have to be able to do this one without graphing calculator. But for right now, it would require a graphing calculator. So we would plug things into the graphing calculator, and so if we do that, if you do that, then you should be getting, and really there's no work to show other than the fact that you just plug it in the graphing calculator. And 3 decimal place accuracy, it's 3.586. Okay, moving on, problem number 4. Region bounded by, I'm going back to the region I used from problem number 1. So y equals the square root of x, y equals 0, x equals 4. But this time we're going to rotate about the line y equals 3. Now, it's so important to make sure that you actually, whatever line that they tell you, it's not always the x-axis or the y-axis. It's so sad when I see somebody who doesn't graph a line accurately. Make sure you know if it's horizontal or vertical. Y equals 3. It's maintaining the same elevation. It's horizontal line, elevation 3. So now, what do we notice this time? Well, first off, we can get perpendicular rectangles, but the rectangles are not going to be touching the axis of rotation, at least not within the region. And so what's kind of going on here is we're going to generate the volume of the whole solid and then we're going to subtract the volume of the hole, because it's like we're coming through and we're going to drill this out, and so that's the volume that we actually want. The volume we want. That's the way we're going to do this one. Okay, so let's go ahead and get to it then. So we've got pi. Okay, now the whole solid, that's going to be this bigger rectangle. So what is that radius? Well, top minus bottom, so 3 minus 0. So pi 3 squared dx, because they're little delta x's. And these go from x equals 0 to x equals 4. So that's the volume of the whole solid. Now, we're going to come through and we're going to subtract out the volume of the hole that we're drilling out here. And so that's the smaller radius that's representing the part that we're drilling out. And so its volume is going to be pi r squared. Now that radius is top minus bottom, 3 minus root x. So pi 3 minus root x squared dx. And again, those rectangles would be going from the x of 0 to the x of 4 as well. Okay, now what do we notice? Well, first off, there's a GCF of pi. And there's a definite integral from 0 to 4 for both of those. And so because of that, we can actually combine these two. So I've got 3 squared minus 3 minus root x squared, and then all of that with respect to x. Okay, now we want to kind of generalize what we're doing here right now. So when we have perpendicular rectangles, but the rectangles aren't completely in the region when they are touching the axis of rotation. So what do I mean by that? So look back to the beginning. The theoretical one, yes, we're touching the axis of rotation, but the whole rectangle is within the region that we're talking about right there. The whole rectangle is within the region that we're talking about as we go from 0 to 4. So when we are doing this one, we have the end of the rectangle, and part of it is not in the region itself. So when we have this sort of situation happening, it's like we're drilling out the hole, and it's this situation right here, the volume of the whole thing, and then we drill out the HOLE in the middle. And so that volume is going to be pi and HB, and it's the big radius squared minus the little radius squared with respect to, it could be with respect to x, or it could be with respect to y. It just kind of depends on which way your rectangles are going. If they're vertical, it's little delta x's. If it's horizontal, it's little delta y's. Okay, and so anyway, this is how we deal with it, kind of a shortcut way. Now, I mean, you could do like what I was just doing right here, where I basically am developing the formula, but it's kind of nice to use the formula here. By the way, this one's known as the washer method. Not washer dryer, but they're talking about washers like nuts and bolts and washers. So you know, it's like we were getting a disc before, but if there's a hole in each disc, think about nuts and bolts and washers. And so then you've got that situation going on. And so that's why it's called the washer method, because you're stacking a bunch of washers. Okay, so anyway, I don't want to spend too much time finishing this one off right now. So we've got pi, that's 9, so it becomes, and sometimes doing a little bit of algebra is a good idea and all this kind of stuff. So 0 to 4, I've got 9, let me do a little bit of algebra here. This is 9 minus 9 minus 6 root x plus x. And if I distribute the negative, the 9's eliminate, and I've got 6 root x minus x dx. So pi. Okay, so we've got root x. Root x becomes x to the 3/2 with a 2/3 adjustment. 2/3 times that 6 is 4. Okay, minus, and that becomes 1/2 x squared from 0 to 4. So we have pi times, let's see, okay, 4 to the 3/2. Okay, square root of 4 is 2, cubed is 8, times 4 is 32. 4 squared is 16, half of it is 8. And then if I plug in zeros, I get 0. 32 minus 8 is 24. This is 24 pi. Okay. Doesn't always come out to be a nice whole number like that. Finally, number 5 here. Let's practice this one more time. I've got a region bounded by x equals y to the 3/2. I've got x equals 8 and y equals 0 are part of the boundaries. So you can see the boundaries here, and we're going to rotate this about the line x equals -1. Now remember, x equals -1. X equals, that's a vertical line. Okay, vertical line. We're rotating about that. We've got, this is that washer method kind of thing. So my big R, right side minus left side, so 8 minus a -1, which is 9. My little r is right here, right side minus left side, so little r is y to the 3/2 minus a -1, which is y to the 3/2 plus 1. Okay, so we're ready to set it up. Our volume, pi. Now my rectangles are horizontal, so they start at the lowest elevation. They start at elevation 0, and they go to the highest elevation in the region, which is 4. So 0 to 4. My big R is 9 squared, minus my little r is y to the 3/2 plus 1 squared, big R squared minus little r squared, dy. Okay, there's the setup. Now we could do this one by hand, but the notes have already been going on here for a while. So let's just go ahead and plug the, well, actually we'll just say, I mean, you could finish it off. We'll just say dot dot.